So in this lesson, what we're going to look at is characterizing the thermal output of a nuclear weapon, and then looking how that thermal output is transmitted through the environment to interact with things like buildings and trees and so on. Now, at the top, I'm going to put two different links here, and that's because this lesson is kind of long. You might not want to do it all in one sitting. So the links are going to be for the thermal source term, and then the second link is going to be for transmission of that thermal energy. Okay. So, quick refresher on electromagnetic radiation. Of course, these diagrams are all from the lesson on photon interactions. We have the electromagnetic spectrum showing us the different energies. All the way at the high end, we've got gammas and hard X-rays moving down through soft X-rays, UV, visible, infrared, and all the way down to radio waves. And then the other two diagrams are the interactions that we're going to be concerned with here. Now, there is a third interaction, if you recall, there's pair production, but the energies that we're talking about for, the thermal effects of a nuclear weapon, their energies are much, much too low for pair production to ever occur. So we're going to go ahead and disregard that. So we're left with Compton scattering, which is our photon comes in, it's got enough energy so where it hits an electron that's bound to an atom, it ejects that electron from the atom, and then the photon goes off with less energy in some other direction. Now the second one is the one we see down below, which is photoelectric absorption. So we get a photon that comes in, the atom is now in an excited state, and the atom can then re-emit a lower energy photon out in some random direction. Now there does come a point where the atoms don't have enough energy to radiate an additional photon. And that's when there's so little energy being carried by that incident photon that it just leaves it in an excited sort of vibrational state. Now the photons that are emitted can be lower energy, so what we can have is UV comes in, gets absorbed, we can get visible light out, we can get infrared out. The same thing happens, visible light comes in, and then that can be transformed into IR radiation. So when we talk about nuclear weapon output, remember that we have about between 70 and 80% of the energy, initial energy of our weapon is carried off by X-rays. Now, once we have the expansion of that fireball, and then we have the shock compression of the air, we see that that energy stops being X-rays and starts being something else. And the two things that it can turn into at lower altitudes is we're going to get some combination of thermal effects, so heat basically, but we're also going to get that energy in blast, that shock wave that we're generating. And if we look at right around ground level ish, there's a caveat to that, right around ground level, if we look at this cool little thermal partition diagram here, and we look here all the way at the bottom, thermal yield is a fraction of total yield. So we've got our nominal X-ray yield, let's call it 70%, right? So here, right at the sea level, if you will, we have about half of it being thermal, about 35%, and then the other 35% is going to be transformed into shock and blast. Now, as we move up in altitude, the air gets a lot less dense. And this has some pretty interesting implications. And if we go up to about 45 kilometers, the air density is so severely reduced from what it is at sea level, we find out that the majority, about 65% of that energy is now thermal, and very, very little, about 5%, is transformed into shock. Again, the density of the air is so small that there's not a whole lot of stuff to push. So you really can't get a good shock wave going because there's just not enough material. And then eventually, if you get high enough in altitude, what you end up having is these X-rays that are being released from the weapon itself, they don't really have anything to interact with at all. So most of the energy is then still retained by those X-rays, with very, very little of it being thermal and absolutely none of it going into blast. So if we look at about 70 kilometers, we see that the thermal yield is down to about 25%, with the remaining, 45% being the X-rays. They're just going to continue on out, and they're not going to transfer their energy. And that's just what this slide says. So what does this mean? Well, the higher altitude or detonation, the less effects we're going to see from both thermal and blast on a target at the ground. Now, that's not to say that if they're that high, they don't matter to us, because they do, because we have aircraft flying, we have, again, we have stuff in low Earth orbit. So it still is important, but it just won't be transmitted to the ground effectively. So we have this variable, this concept of the thermal partition, and it's just what that graph showed. And it just tells us for a given set of parameters how much of that energy is going to be thermal. And so it's a function of not only height of burst, but also how much energy did we release? What was the size of the weapon? So we have here on the left-hand side, we have height of burst in kilofeet, so thousands of feet. And over on the right side, we have the total yield of the weapon in kilotons. So what we can see is a height of burst up to 15,000 feet. With a 1 kiloton yield, we get 35%, 10 kilotons, 100 kilotons, a megaton, or even 10 megatons. It's still that 35%. That's half of it's going to shock and half of it's going to thermal. Now, as we start to increase in altitude, we start to see things change a little bit. So if we look at 50,000 feet, for a 1 kiloton, it's still just 35%. At 10 kilotons, though, we start to see that shift more towards thermal and less towards blast. Again, the density of the atmosphere coming into play. If we move all the way up to 10 megatons, we see that we've gone from 35% to 42% being carried away by thermal. Now, if we go all the way up to 100,000 feet, again, with a 1 kiloton, we've moved up to 40% being carried away by thermal. And then if we look at 10 megatons, we're at 45% being carried away by thermal. So this handy-dandy little table is in the effects of nuclear weapons. It's table 788. And this thing's a good handy reference to say, okay, well, if I have a height of burst of something and I have a particular weapon yield, then this is what I can expect for thermal effects. Now, this is a diagram we've seen before, but it looks a little bit different because this is on a linear scale rather than the log-log scale that we saw before. And I'll have that plot here in a second. So this is that double pulse. And so we see the first pulse that's emitted from the weapon detonation only carries about 1% of the thermal energy. It's mostly UV, so we don't really get to see it, but we see, some of that light very briefly. Very short duration, and again, once that shock wave happens, then we don't even see that anymore, and that's why it falls off very, very rapidly. And then, of course, the second pulse that we get carries away 99% of the thermal energy, and it's a much longer duration. And this duration is, again, dependent upon the yield, as I explained in the last lesson. So if we have a small yield, it happens very quickly, about half a second. But as we move into like megaton range, that gets stretched out from half a second all the way to 20 seconds. And again, this is that reason that we discussed before, that the amount of radiant energy required to ignite paper or wood or something like that, it actually goes up with increasing yield because it's stretched again over a much longer time period. So, apparent temperature. Now, there's a couple things on this slide that you just need to be aware of. We have two different regimes we're looking at, below 15,000 feet and above 15,000 feet. Okay, and there's that cool graph, but this time it's on the log-log scale, so it doesn't look quite as different as the one we saw before. And what we end up seeing here is we're looking at the maximum amount of power being produced by our weapon detonation, and the what's called the Tmax. And the Tmax is basically after that shock front has become transparent to the photon energy shining from that from the inner fireball. The peak of where that occurs is called Tmax. Technically, it's called T2 max, with T1 max being right here, but that's not super important for us. So we have a maximum amount of power below 15,000 feet, and our Tmax we can calculate based on the weapon yield. And above 15,000 feet, we have similar expressions, but they're modified to account for the change in density of the air at different altitudes. And so we have the rho h, which is the density at whatever the height of burst was, and then we have rho 0 or rho naught, which is the density of air at sea level. So what we're going to do in order to account for the air density changes is we're going to take a ratio of those two things, and that's going to be a factor that we're going to use, or that we can use in this particular equation. Now you're probably asking yourself, how do I know that? How do I find that? How do I estimate what's this ratio of density at altitude versus density at sea level? Well, as luck would have it, you don't have to estimate it. There's handy dandy tabulated data sets, and this is obviously table 7.85 from effects of nuclear weapons, and it gives you, for a given altitude from 15,000 all the way up to 100,000 feet, what is that change in density? What is that ratio? So if we're at 15,000 feet, it's better than half the density of sea level. But if we start looking at, if we go all the way up to 100,000 feet, we see that it's just a small fraction. It's 1.4% as dense as it is at sea level. And this, again, because there's not that much stuff around, your shock almost completely vanishes because you've got nothing to compress, right? There's just no material there. And so you see a huge amount now of thermal radiation being the primary mechanism for the energy dispersion. So let's take a look at this graph. Now, this is in your book. It's figures 7.84, and it does a couple of different things, or allows us to see a couple of different things. Now, we're going to calculate using those formula that we saw before. We're going to look at Tmax, Pmax, and then the total energy being carried away by thermal. Now, the T over Tmax and P over Pmax, which is the normalized time and the normalized power, is something that we're going to talk about here in 1 second. So first, let's just get some stuff out of the way. So for our weapon yield, we're going to go ahead and use 150 kilotons. So if we look over here, we just plug in 150 for W, and we do that calculation, and we get 0.378. Okay, for Pmax, we do the same thing. We just go ahead and plug 150, raise it to 0.56, and we're going to end up with 52.6. And that's in kT per second. Okay, and then finally, the total energy that's being carried away by the thermal term is simply going to be, we're going to assume that this happened below 15,000 feet, so we're going to get that half split, that 35% being carried away by thermal, of course the other 35% by blast. So we just multiply 0.35 by 150, and we end up with, hilariously, almost the very same number, 52.5 kilotons. Okay. Now the weird thing is that when you're doing these calculations that require this chart, you're looking for something at a particular instance after a weapon detonation has occurred. So you're looking for something in time. So the first thing we're going to look at is that T over T max. So we're going to pick some time after detonation, okay, and then we're going to calculate what that ratio is from that time to T max. And in this case, just to make things simple, we're going to look at 1 second after detonation. So therefore, if we go over here to our T max, As soon as I can find my cursor again. There it is. So now we have 1 divided by this 0.378. So that's going to give us a ratio of 2.65. Okay, so that is our calculated T over T max at 1 second after detonation. So we're going to come over here to our cool little graph. Now our graph has these 2 different curves. And you'll probably notice that there's an axis here and another one over here. So you're probably asking yourself, well, which one do I use? Well, the curves have this arrow on each of them that points to which axis they belong to. It's pretty much that simple. And do pay attention to it because we're going to see this on a lot of the different plots throughout this course. All right, so we're going to start here on the x-axis, and we're going to say that this dotted line that goes up vertically, it's about 2.65. Sure. Now, why are we drawing that vertically? Well, because we're going to be looking for the intersection points to both of these plots. So if we wanted to determine at that ratio of T to T max, what is the P to P max ratio, we just look at where it intercepts this curve, which is right there, and we just draw a horizontal line all the way over to the axis here. That's about, I don't know, 0.27, 0.2, we'll call it 0.25, sure. Make things easy. So now we have some new information where we have 0.25 for our P to P max. So now we can solve for the power, instantaneous power, thermal power at that 1 second point. All right, so all we're going to do is use the equation that we already have, and we're just going to solve for P. So P is going to be equal to, let's see, shit. So now all we're going to do is solve for P using a little bit of algebra. So we have 0.25 is going to be equal to some P. We know what our P max is. Okay. So therefore P is going to be equal to 0.25 times 52.6. which is going to be equal to 13.12. And that's, of course, in kilotons per second. So that is our instantaneous power output at 1 second. So now what's this E over E total thing? Okay, well, what we know is that we can determine at any point using the PP max what's the instantaneous power output. But what we might be more interested in is how much energy has been output to that point. So if you're familiar with calculus, that E over E total, which is going to be the axis over on our right-hand side, that's simply the integral of the power curve. So how much energy have we produced up until that point, that 1 second? So all we do again is we take and look at our cool little dotted line, see where it crosses here, draw a horizontal line to this axis, okay, and then we can estimate it, we'll call it about 55%. So we'll call it 0.55. Using the same algebra shenanigans we just did up here, we can go ahead and calculate the total amount of energy that has been produced to that point. And again, we're talking about thermal energy by a 150 kiloton weapon is going to be 28.9 kilotons. Okay, there's the math. Now, you're probably asking yourself, what does any of this matter? Well, what we need to know sometimes, especially when we're looking at how things are going to be affected by these thermal effects, is, well, what time are we looking at? So we want to know what's the thermal energy, thermal power being output 1 second after the detonation, in terms of kilotons per second. And this changes depending, of course, at what time period we're looking at. More importantly is how much thermal energy has been radiated or produced from this weapon detonation at that 1 second point. And we find out it's actually, a good fraction of the yield, that stems from the X-ray yield. So we have a total fraction being carried away by thermal of about 52.5 kilotons. By 1 second, more than half of it has already been produced. So this is quite quick. So that means that all of this, thermal radiation of 28.9 kilotons, this energy has already been produced at that 1 second mark. That's all this is. That's all this is for. These calculations and this plot are just to determine instantaneous power output and total amount of energy produced at some given point in time. And it should be obvious from the plots that as we move in time, our P over P max decreases rapidly. But our energy is still going up, our total energy. So instantaneous power is quite high at the very early stages, but drops off rather rapidly, which correlates to a rise in energy being produced very high or very quickly at earlier times, and then sort of tapering off and not gaining a whole lot as you move into further times away from the moment of detonation. Okay, so we're going to take a pause here, and we'll resume after this little interlude. So what did that have to do with anything, that stuff we just talked about? Well, so we've been able to characterize our weapon in terms of its thermal output. But that thermal output doesn't really mean anything to us unless we think about it in terms of what is it going to do to stuff. And by do to stuff, I mean, impart energy to people or buildings, anything in the environment. Now, the energy output of the weapon is definitely not the same as how much energy is imparted into the stuff that the thermal radiation hits. And the reason for this is it has to do with distance, and it has to do with how this energy spreads out as it expands spherically. So the best way I can demonstrate this is with this cutaway version of a sphere. Now, the surface area of a sphere is 4 pi r squared. So you can imagine that the thermal output of the weapon could be measured at the surface of this expanding sphere in terms of energy per area, or energy per, in this case, we're going to use centimeters squared. Okay? So imagine that our radius is 1 centimeter. Okay, so the surface area where all our energy is basically located is going to be 4 pi centimeters. Right? Well, 4 pi centimeters squared. Now, if we just double the radius to 2, right, our R term is now 4. So now we have 16 pi per centimeter, or centimeter squared. And then if we go out to 3, so then we have 9. So now we have 36 pi centimeter squared. So what's happening is as we get this spherical expansion, right, the amount of energy available for any given square centimeter starts to go down. And it's because we're increasing the size of the surface exponentially as we're moving outward. So what does all that mean? Well, the cool little expression, the math that I got right here, is that the energy for as a function of radius that we have is going to be the output of the weapon, and it's going to be divided by the surface area. So we have the same amount of energy, whether it's compressed into that initial, couple meter, sphere as it starts to vaporize the case and then escape into the atmosphere. But that same amount of energy, which may be hundreds and hundreds of watts per square meter, when we take that same sphere and we expand it outwards, the amount of energy per given area goes down quite significantly. And so we can account for this by simply dividing our output term, in this case, the thermal output of our warhead or our weapon. We divide that by this spherical expansion term of 4 pi r squared. So the further away we get, the less energy there is per area. So, is there anything else that we need to know about transmission? Well, we have absorption. So basically we can have some of this energy decrease in intensity because it's depositing some of its energy in the intervening material. Okay, imagine the shock wave's done. We still have this thermal energy that's being transmitted, but it's still going to interact with the stuff in the atmosphere, like molecular oxygen, ozone, and nitrous oxide. So it's going to be absorbed and re-emitted. It's going to lose some of its energy. So it's going to be a lot less than it was before. We also have scattering. Again, comes in, bounces off an electron, loses some energy, goes off in a different direction. Now, most of this in the visible range is the scattering. It doesn't really lose any energy. It just changes direction. It just goes somewhere else. And this is Rayleigh or coherent scattering. So this is characterized by what we would call visibility, right? So this is a horizontal distance at which a large dark object on the horizon has sufficient contrast to be discernible in daylight. And this is a function of scattering, because if the photons are being scattered a lot, then many of them aren't going to make it from the object to your eye without bouncing all around and sort of decreasing the visual fidelity, if you will. And again, this is affected by molecular oxygen, molecular nitrogen in the air. So as we move further away and we get increased scattering, the ability of us to separate an object from the background becomes severely diminished. That said, you can also have ways of those photons getting to your eye, if you were looking at something, that normally wouldn't be able to happen. And that's what that little diagram with the eye is showing, is that you can have something directly shield between you and the source of the photons, but because of scattering, some of those photons will actually still be able to get to your eye because they will bounce over, around, and underneath whatever is blocking or whatever's in the way. So you can still end up getting photons from a source even if you have a shield in the way, simply because of the scattering. So it's kind of a double-edged sword. In some respects, it reduces photons from the source that are getting to you or anything. But in some ways, it reduces the effectiveness of something that you put in the way because it can scatter around it. Unless, of course, you put yourself in a box, and then you're probably okay. No photons from that source will get into you because there's no way they could do it. But if you just, say, had a freestanding wall or something, then yeah, you can still get hit by photons that you normally wouldn't have expected to get to you. And this is important when we talk about where is this energy coming from and how effective are certain types of shielding. Okay, so how far is far enough? Well, if we talk about visibility of the atmosphere, we look at how far away can we discern things that separate from the background. So if it's exceptionally clear, this happens at about 170 miles or 280 kilometers. Very clear, okay, it's cut down by a significant amount to 50 and 31. And then just regularly clear, what we normally think of as clear for sort of everyday atmosphere, it's about 12 miles visibility. Now, That gets reduced when we start introducing things into the atmosphere, like particulate matter, smoke, and dust. Also water vapor in terms of fog. So when we put a light haze is a little bit of moisture. This whole chart is basically built around moisture. A light haze is a little bit of moisture in the atmosphere. Nothing too drastic. Visibility goes from 12 miles down to about 6 miles. It's not something that you would really notice on an everyday basis, unless you had were used to very long, clear sight lines. Now, regular haze, this is moving from a little bit of moisture to the intermediary before we get to fog, which cuts our visibility down again by quite a bit. Then we get to thin fog, which is, visibility is a mile-ish, maybe a little bit less. And then we get into heavy fog, which is a regular fog, which is about half a mile visibility. And then, of course, as you can see in the photograph here, then you have what we call British fog, where your visibility is cut down to tens of meters. So this visibility, it does have an effect on the transfer of the energy from the thermal part of our weapon detonation. And it should make sense, because the more stuff is in the way, the more that thermal radiation is going to interact with the stuff in the way and lose its energy before it ever gets to us. So at about 30 miles altitude, what we're going to see is that the air density is like 1,000 times less, 10 to the -3 than what it is at sea level. So that means the distance that our thermal radiation can travel before it interacts with something is going to be about 100 to 1,000 times greater than it is at sea level. So what does this mean? It means that our fireball, as we go up in altitude, gets much, much bigger. So we can go from, hundreds of feet to thousands of feet at altitude. So it's quite impressive, just the difference, the density of the air can make on the output of a nuclear weapon. So we have this spherical expansion, which reduces the amount of thermal radiation that's going to get to us, and it varies with distance. And then we have some stuff that can be in the way. But there's a couple other things that we need to account for. The distance part we can account for by this plot right here, which gives the tau, or transmittance factor, and it's based on how far you are away. So on the vertical axis, we have the height of burst. On the horizontal axis, we have distance from ground zero, horizontal distance from the detonation. So if you had an air burst at 10,000 feet, if you took the point where the weapon detonated, drew it straight down to the ground, and then drew a horizontal line to wherever you're interested in, that's the horizontal distance. So we'll talk about the slant range and a little bit of the trigonometry that goes along with this here in 1 second. So what are we seeing? Okay, well, this particular plot just says, if I know my height of burst and my distance from ground, I can tell you how much of this thermal radiation is going to end up being transmitted. So let's just pick something at random. Let's look at 100,000 feet away at, roughly 100,000 feet height of burst. So if we go right to here, so here's 100, here's 100. So the closest line is going to be a transmittance of about 80%. But it's not quite there. It's just a little bit below. So it's right about here. But it's much closer to that than it is to this line, which represents 70%. So we're going to say this is probably somewhere 78, 79% transmittance. Okay. So again, if you have the distance and the height of burst, you can figure out how much of that stuff's going to get to you. That's all that this says. Gets a little weird when you get really close, and that should make sense. The closer you are, the more that radiation is going to get to you, because it doesn't really have any place, or it doesn't have that much distance or material to get through to get to you. So, if you're talking about like you're standing and it detonates like right next to you, then yeah, all of the thermal radiation is going to hit you, but that's probably not going to be that big of a concern to you, at least after a millisecond or so. Now, this is for a clear day. So if you remember to the table that we just looked at, clear day is about 12 miles visibility. Now, tau is complicated, and it gets more complicated the more stuff is there, the more intervening factors have to be included. So they usually do some pretty serious computer modeling to take into account like atmospheric contaminants, dust and dirt, and even moisture. Now, here's something that's weird. The layer of clouds that may or may not be present, and something like snow on the ground, these have a lot to do with this thermal transmittance. And here's a good reason why. They reflect. So imagine that you have a height of burst. Okay, your height of burst is here, cloud cover's up here. Okay, so a lot of those photons, remember, they scatter, they're low enough energy, so especially in the visible range, they just scatter around. So photons that would normally be escaping through the altitude, because it gets less dense, so there's less stuff for it to scatter off, so most of them are going to continue on up. Now you get this big, thick, heavy water vapor. And what this is going to do is this is going to provide a huge amount of scattering back down towards the ground. So when we talk about transmittance, if there's a heavy cloud cover and the burst is below it, then you have to basically multiply your transmittance by a factor of 1.5. Now, similarly, if you have an altitude burst and you have some snow on the ground, that snow again is going to want to reflect or scatter back those photons that would be hitting and normally be absorbed in the material of the ground. So now you have to once again account for that, and it's about a factor of 1.5. Now, in the worst case scenario, what happens if your weapon goes off, there's snow on the ground and clouds above it? Well, then you get 1.5 factor scattering from here, 1.5 factor from scattering here, so you have to increase your transmittance by a factor of 2.25. So you can, the environmental conditions can really change how much thermal energy gets to a specific location or a specific target. Now, if your height of burst is above a cloud cover, then very similarly, you're going to reduce the amount of thermal radiation that you would expect to get by that factor of 1.5. Okay, now we come to the maths. Okay, exposure distance relationships and again, this is just for air bursts in the atmosphere, not underwater, not underground, not in contact with the ground, because that's something completely different, and not exoatmospheric. So thermal radiation gets attenuated again as it scatters around and bounces around and loses its energy on its way to wherever it is you're concerned about. And we can figure out what that is based on the distance away, the transmittance factor, and of course the altitude correction factor, F. So the figure I just showed you assumes a visibility of about 12 miles below 15,000 feet. However, if you want to be more accurate, then you can use the tables 7.88 and 7.101, which gives you that density correction factor, that F, the thermal partition factor. And we can come up with two equations. One has distances in thousands of feet, and the other has distance in miles. And the numbers that are in front on the numerator of both equations account for, we'll call it conversion factors. That's basically what they're there for. So remember when I said we have the height of burst and we have the distance away. So the total distance then between what you care about and where the weapon detonated is called the slant range. And if you remember back to some geometry, if you have a right triangle, the hypotenuse that connects the adjacent and opposite legs, that's the slant distance. I mean, it really is nothing more than that. And it's a pretty straightforward calculation if you have the height of burst and the distance away to calculate what that slant range is, because that's the total distance that the thermal energy or the thermal radiation has to travel to get to you. So, of course, the longer the distance, the more energy it loses and the less of it actually can get to you. Okay, so again, this is brought to you by the letter Q, which we're using again in sort of a different fashion than we did when we were talking about doing the mass defect and energy release for a fission reaction. They tend to reuse a lot of letters in physics and in calculations like this. So don't get them confused. I don't really see how you could, but just be forewarned. Okay. So now let's look at how to bring this all together. Using that cool little formula that we have, that Q, I've got them both up here. All right, so we're going to look at a 20 kiloton weapon that's detonated at a height of burst of 4,650 feet with a 2,500 ground range in feet. Okay, so the first thing that we need to do is we need to find what's our slant range. Okay, so we know the height, we know the distance. Let's go ahead and see if we can figure that out. Okay, so for those of you that, again, may or may not remember, old Pythagoras here has this cool formula for telling us the length of a hypotenuse if you knew both the opposite and adjacent sides. So if I know this, I know this, I can calculate this. Okay, so we're going to just do some algebra here. Basically, we're going to take the square root of both sides so that we can get that C all by itself. Okay, so then we can plug the numbers in. Again, we're just working in feet. So I said it's 4,650. Okay, and we're going to add to that the 2,500. Okay, and that's going to be equal to 5,280 feet, which we're going to say 1 mile. So we have nice smaller numbers so that we can use this formula right here. All right, so now we know that C, which corresponds to our distance. Okay, so we have that. All right, now what's the next thing that we need to do? Okay, so the next thing we need to do is say, all right, well, what's our thermal fraction? And again, we're only at a height of burst of 4.6 kilofeet, which is well below 15,000 feet. So we can go ahead and assume that our fraction is going to be, again, our 0.35. Okay, so we have W, we have the yield. We have D, which we figured out. We have F. So now the last thing we need to do is find what tau is. So again, we're going to go to our cool little graph here, and we're going to say, okay, well, where are we here? So this, again, this is in tens of thousands of feet. So this is that's 50,000. Stop that. 50,000. Okay, so this would probably be 25,000, and then 12,000. So we're going to be way down in here. Stop that. Okay, so we're just going to assume that it's basically right on top of us. And again, same thing happens with the distance from ground zero. We're only 2,500 feet away. So this thing is basically exploding right on us. So we're going to go ahead and say that our tau is going to be just equal to 1. Okay? All right, so now we can go ahead and plug all of our numbers in. So we're going to get our Q is going to be equal to 3.07 times 0.35 times 20 times 1, all divided by 1 squared, which is still 1. And so then we're going to get a total value of our thermal energy at 21.5 calories per square centimeter. Okay, that's pretty much it. Again, there is some math. We can't totally get rid of the math, but we can do some pretty simple calculations to get a rough estimate, given distances away, weapon yields, atmospheric conditions, to where we can say, all right, this much energy at this distance away from this particular weapon, which we need to know when we talk about, well, what is that energy going to do once it hits the thing it's going to hit, right? So we're going to be dumping energy over time into materials, and we're going to see whether or not they're going to ignite or they're going to char and immediately, like catch fire or warp or any of these things. Okay, so let's put this all together and let's try it out with a graph instead. Now, this particular graph has some limitations to it, which are here on the left-hand side. So it has to be below 15,000 feet, but has to be above some arbitrary height limit based on the weapon yield, which is related to optimal height of burst. So we'll talk more about that a bit later, but you can plug the numbers in and see if it fits where it should. So if the height of burst is below that particular expression or above 15,000 feet, we have to go back to that equation we just did to find out, what the radiant energy is going to be, or thermal energy. So in this case, we have our 20 kilotons, which is right here. So we just draw a vertical line. And then we look over here, the slant range that we calculated, we found out it was a mile, approximately. So then we are going to draw a horizontal line, and then we're going to look at where do they meet. Now, we'll notice if you read these numbers attached to these lines, they are decreasing as you move up the y-axis. So the closest line is about 26 calories per centimeter squared. We're not quite there, but the next further line is 12 calories per centimeter squared. So we're much closer to the 26. So we can just kind of guesstimate how close we are, given that the distance between them is a total of about 14. So what fraction of that is this? So again, it's just a guesstimate. So I would say somewhere, I don't know, around between 20 and 23 maybe, which really goes well with what we calculated of 21.5. So we calculated exactly, but we can use our graph if, again, our weapon falls within these very strict parameters with respect to height of burst. We can just estimate it by drawing some lines on a plot. So more than one way to estimate these things that we're interested in when we're talking about nuclear weapon effects. Okay, so that's it for this lesson. In the next lesson, we're going to look at what are the effects of this thermal radiation on materials and objects. So until then.